In this video, we're going to talk about trees. And for that, we're going to need several definitions. So let me start. A graph is called simple if it has no loops or parallel edges. And a graph is said to be circuit free if and only if it has no circuits. And then a graph is called a tree if and only if, to make that a little bit better, it is circuit free and connected. So a graph is called a tree if and only if it is circuit free and connected. And there are several examples that you could think of. A tree, something real simple would be just something like that, would be a tree. Though usually we think of what you might think of like leaves and stuff on a tree. Yeah, maybe like something would look like this. That would be a tree. Or it could have something more extensive, maybe like this. Maybe some of these go out here. Those would all be examples of trees. We have these vertices, the dots of the vertices, and the straight lines of the edges. You can't have a circuit. It has to be circuit free, and it has to be connected. If it's not connected, it's not a tree. If it's not connected, or if you have a circuit, it's not a tree. And they also have something called a force, which we probably won't use too much. A graph is called a forest. If and only if it is circuit free and not connected. If it's circuit free and connected, it's a tree. If it's circuit free and not connected, it's a forest. So you could have maybe something like this would be a forest. Maybe have this. I guess maybe the idea of the definition of forest, it has, more than one tree. As I said, we're probably not going to use this too much. Another definition is a leaf. Or sometimes called a terminal vertex, is a vertex of degree 1. And so you can see what we drew over here. Let's look at some of these. This would have degree 1. This has degree 1. Now, normally, again, it's called a leaf because it would be like at the end of the tree normally. Now here, this leaf is at the beginning, but you'd sort of think of a leaf being at the end of a tree. So again, things that have degree vertices have degree 1. This has degree 1, this one, this one. These are all leaves or terminal vertices. Same thing over here, leaf, 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 like that. So that's a leaf or terminal vertex is any vertex that has degree 1. An internal vertex also called a branch vertex is a vertex of degree greater than 1. So again, that's called an internal vertex. And once again, you can look back at the examples here. Like this is an internal vertex. So is this, 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 and even this, because they have degree more than 1. This, excuse me, not that one, but this, this, all have degree more than 1. And so now have some theorems. Any tree that has more than 1 vertex has at least 1 vertex of degree 1. So any tree that has more than 1 vertex has at least 1 vertex of degree 1. and this is a very important theorem for identifying a tree. For any positive integer n, any tree with n vertices has n minus 1 edges. For any positive integer n, any tree with n vertices has n minus 1 edges. So again, this can be used to find out if a graph is a tree. So again, it's saying any tree, if it's a tree, first of all, starting off, if it's a tree and has n vertices, then it has one less edge than vertice. And another theorem. If G is any connected graph and C is any circuit in G, and any one of the edges of C is removed, from G, then the graph G remains connected over the new graph. And so what this kind of means is, let's say you have a graph. Again, it's a connected graph. And maybe you have like a circuit. In this graph, and let's say you might have something out here, here, here. Maybe you have something like this. So this says it's a connected graph, and you can say identify a circuit. Let's say this circuit right here, if we remove any edge on that circuit, the graph will still remain connected. You can see that if we took away this edge, it would still be connected. If you took away this edge, in other words, if you, of course, just take one of the edges away. So if you took away this edge here, the whole thing would still be connected. You could still go from any edge to, or excuse me, from any vertex to any other vertex to still remain connected. Or if you took this one away, you could still get from any vertex to any other vertex. So you can take one edge away from any circuit and the graph will still remain connected. And the same thing over here. Here's a circuit here. If you took away this, or this, or this, or this, or this, any of the edges in that circuit, you would still be connected. Now, over here, so you can't take this one away or this one away because they're not part of a circuit. These edges are not part of a circuit. So you can't take those away. If you did take those away, it wouldn't remain connected. But if you take an edge away from any of the circuits, it will in fact remain connected. And here's a theorem related to a previous one. In the previous one, we start out by assuming you had a tree. Now this one says if G is a connected graph, with n vertices, and n minus 1 edges, then G is a tree. So if it's a connected graph with n vertices and n minus 1 edges, it is a tree. Again, it's important. It has to be connected and have these to be true. Here's another theorem. If G is any graph with n vertices and m edges, where m and n are positive integers, and m is greater than equal to n, then G has a circuit. So if G is any graph with n vertices and m edges, where m and n are positive integers, and m is greater than or equal to n, then G has a circuit. And notice, again, this this applies to any graph. And same thing with this next theorem. It applies to any graph. If G is any graph, then the total degree of the graph equals 2 times the number of edges. 2 times the number of edges in the graph. So let's keep all these theorems in mind, and let's go through some problems here and see what we can come up with. And again, by going through some problems, it kind of gives us a better understanding of what we have. So what I think I'm going to do is write down several questions, and then I'll go through the answers. So for these, draw the graph, or explain why it does not exist. So number one's, say you have a graph with 4 vertices and 2 edges. So is it possible to have that? And if it is, go ahead and draw the graph. If it's not possible, explain why it's not possible using, say, some of the theorems we've looked at so far. And number 2, a tree with 5 vertices and 4 edges. Number 3, connected graph with 10 vertices, 9 edges, and has a circuit. Now let's look at number 4. The tree has 10 vertices, 10 edges, a tree, 10 vertices, and total degree of 20. Next, we have a graph, 2 vertices, 1 edge, but it's not a tree. Is that possible? And let's go to another one here. Number 7. A graph. It's connected. 5 vertices 7 edges. Go to number 8. A connected graph has 20 vertices, 19 edges, does it have a vertex of degree 1? Number 9, a connected graph has 15 vertices, and 17 edges. Does this graph have a circuit? Finally, number 10, you have a graph. It's circuit free, has 5 vertices and 2 edges. So take a look at those 10 questions and again, see if you can find a graph or answer the question, otherwise answer the question. Or if you can't find such a graph, explain why using the theorems that it doesn't exist. So what you can do now, you can stop the video if you want and work on all 10 of the problems and then restart the video and I'll go through the answers, or you can just try one problem at a time and watch the answer on the video. It's up to you. But you can stop it now if you like. Okay, hopefully you stopped the video and worked on those problems. Now we're going to go through these and show the answer. Like I said, you could either do them one at a time and stop the video between each answer if you'd like. And let me get a little bit organized here. So again, the first question asks us to have a graph 4 vertices and 2 edges. And so let's say we have 4 vertices. Two edges. Now it doesn't say it had to be connected, so we can just maybe do a graph, something like this would work. And there are other options, or you could have just said something like this. So this one has 4 vertices, 2 edges. This one's 4 vertices, 2 edges. Doesn't say anything about being connected. So this one, yes, we can actually make a graph for that one. How about 5 vertices? It's a tree, 5 vertices and 4 edges. In fact, we have a theorem that says if we have a tree and we have n vertices, it'll have n minus 1 or 1 less edge. So this is for sure. We can do this just based on our theorem. And let's actually make, and there, once again, there are many options. On most of these, there are many, many options that you could pick. You could do this. Or again, there's several others as well. But that's just one possibility. So that one can be done. So now this one says we have a connected graph, 10 vertices, 9 edges, and you have a circuit. Now this one's going to be no, because by the theorem, a connected graph with 1 less edge, n minus 1 edges with n vertices, 1 less edge than vertex is a tree, and trees have no circuits. So that one, no. So by this information here, this has to be a tree. It's connected, 1 less edge and vertex. It has to be a tree, but a tree by definition has no circuit. So this one's no. So the next one says a tree has 10 vertices and 10 edges. Of course, right away we can say no, because by the theorem, a tree with n vertices has n minus 1 or 1 less edge. And this one, the tree has 10 vertices and total degree is 20. Now we're going to have to use that theorem that we had a minute ago, which says the total degree of the graph is equal to 2 times the number of edges. So if we have 10 vertices, excuse me, if we have a total degree of 20, if we use this equation, so this means we have 10 edges. So a tree with 10 vertices, much like the last problem, has only 9 edges. So once we established, using this little equation here, once we established that we had 10 edges, then we really are using problem 4, which had 10 edges and 10 vertices, and make the same argument. So this one was no. How about a graph that has 2 vertices and 1 edges, yet it's not a tree? Two vertices and 1 edge and not a tree. So is it possible to come up with something like that? And now, normally you'd think, okay, 2 vertices and 1 edge. That's the definition of a tree. We have n vertices 2 and n minus 1 edge 1. So that has to be a tree. However, it doesn't say anything about being connected. It doesn't have to be connected. There's nothing about connected here. So you can make something that has these properties that's not a tree. You'll have to use like a loop here. So we have 2 vertices and 1 edge. And it, of course, is not a tree. So this one, you can have it. Now, if it would have said it connected, it would have been impossible. But because it said nothing about connected, you can have something with n vertices, n minus 1 edge, and it's not be a tree. And this is one example. Next one is a graph. It's connected, 5 vertices and 7 edges. And yes, we can do this because what you can sort of think of is, so 5 vertices, you could even maybe start with, like, say, a tree of some kind. And I don't know where you want to put the other. You could maybe do something like this. So that's a tree. We have 1, 2, 3, 4, 5 vertices, 1, 2, 3, 4 edges. So you can start with that and then just add edges wherever you like. Maybe add an edge here. You could maybe add, I don't know where you want to go, maybe add an edge here. And maybe add an edge here. So 1, 2, 3, 4, 5 vertices. 1, 2, 3, 4. Let me count. Sorry. 1, 2, 3, 4, 5, 6, 7 edges. So this one is yes. Because it doesn't say anything about being a tree. Of course, you couldn't have a tree with these properties, but didn't say anything about being a tree. So yes, this one is possible. So take a look at number 8. A connected graph has 20 vertices and 19 edges. Does it have a vertex of degree 1? So by theorem, we can say connected, 20 vertices, 19 edges. By theorem, we can say it must be a tree. And then once you've established it's a tree, we have another theorem. Remember, by theorem, any tree has at least one vertex of degree 1. So this one, answer this one was yes. First, using the one theorem to establish we have a tree. And then once you have a tree, use another theorem to say any tree has at least one vertex of degree 1. Number 9, a connected graph has 15 vertices and 17 edges. Does it have a circuit? And the answer is going to be yes. So, and you could sort of argue it this way. A connected graph with 15 vertices that has more than 14 edges is going to have a circuit. So again, if it had 14 edges, it was connected, it would be a tree. If it has more than 14 edges, it's got to have a circuit. Finally, number 10, a graph that does not, that's circuit free and 5 vertices and 2 edges. And this one is pretty easy. Similar problem number 1, really. Like there's no many other possibilities. You could just mark down, 5 vertices, put 2 edges really anywhere you want, as long as you don't make a circuit. And so the answer to that's yes. So that's some problems that kind of give us some feel to how to work with these theorems. And many of the concepts that we need are right among what we just did. And so let's move on. Next, we're going to discuss rooted trees. Rooted tree is a tree that has one vertex that has been distinguished from all others and is designated the root. So you have a tree and you pick one particular vertex, you say, we're going to call that one the root. And then we can also say that there is a unique path from the root to any vertex in the tree. So I could say the main idea is that you designate a particular vertex and say, okay, this is going to be the root. And again, you have many choices that you can pick to designate as your root. So, so again, let me note this example. Many choices. For the root, though, you always pick one, and that's going to be your root. And then you have to designate. So let me say if you have a graph something like this. And usually you'll put your root like at the top here. So let's say here, the root, we're going to call it V1. We're going to designate V1 to be the root. Now you can rearrange the graph to pick really almost any other vertex. So let's rearrange. Let's call V2 the root. Let's say instead of picking V1 to be the root, let's call V2 root. So let's actually, and like I said, we can just sort of rearrange this, keep the graph the same, but just kind of put V2 up here, V5 here, V3 here, and then we'll just move like V1 down to here. Then what V6 will be here. V7 will be here. And V4 will be here. So notice the graphs are isomorphic. They're really the same graph. I've just kind of rearranged things a bit. So see, V2 still has these right below it. And then V1, I've just sort of just pushed it down here. And it still has V6 below it, and then V6 and V7, V4 here. So you can pick almost any vertex and designate it as the root. So now let's come up with some other definitions. The level of a vertex, say called vertex V, is the number of edges in the path from the root to V. So that's called the level. So you look and see, okay, how many edges are there between the root and V, and that's going to be called the level. We'll look at some examples here in a minute. Then the height of a rooted tree is the length of the longest pass from the root to any vertex. So again, look at it, say, look at the root and see, okay, what's basically what vertex is the farthest away, and see how many edges it takes to get there. And that's called the height of the tree. Once again, where the length is measured in the number of edges. Another definition, the children of a vertex, call it V, are those vertices adjacent to V and are one level farther away from the root than V. So the children of a vertex tree are those vertices that they're adjacent to V and are one level farther away from the root than V. Again, well, you can, let me just do an example real quickly here. Let me do maybe, let me call this time maybe V5, call that our root. And we just call this V1, V2, V3, V4, V6, V7, V8, V9. And if that 8 is clear here. So once again, say the children of V5 or V6 and V1. Say the children of V8 is, there's only one child, I should say the child of V8 is V9. Once again, because if you look at V8, see what's below it and just one away, V9. So children or child of V1 is V2. Once again, look at V1, see what's just one away from it. And children of V2 are V3 and V4. Once again, just look at V2 and see the ones right below it just one away, but yet farther away from the root. So we've designated, I should have marked this here again, this was the root. And you can look at any one. Now V9 has no children, V7, V4, V3, none of these have children, but the others do. So let's continue on with more definition. If W is a child of V, then V is called the parent of W, which kind of makes sense. Two distinct vertices that are both children of the same parent are called siblings. Kind of makes sense. So if two distinct vertices, they're both children of the same parent, they're called siblings. And finally, given two distinct vertices, V and W, if V lies on the unique path between W and the root, then V is called the ancestor of W, and W is a descendant of V. Once again, this is, sort of like a family definitions, as you would have like in a family tree. Let me write this a little bit better. You have an ancestor and a descendant. In fact, let's look at one of the, let me take a quick look at this drawing we had here a minute ago. It says if so V lies in the unique path between the root and W, then it's an ancestor. Like, for example, if you look over here, V1 is the ancestors of anything below here. Like, for example, V1 would be the ancestor of V4 because it's V1 is above V4, ancestor of V3, and it's the ancestor of its children. In this case, it's child V2. So V1 is the ancestor of all these. And V4, V3, V2 are all descendants of V1. Same thing over here, like V6 is an ancestor of V9, V8, V7, and V9, V8, V7 are descendants of V6. And you can even go farther down. You could say like V8 is an ancestor of V9, and V2 is the ancestor of V3 and V4. And so that's the definition of ancestor and descendant. And so let's look at an example. So let's take a look at an example here. Let's say, let me put this V not up here. Let's call this the root. Say we have V1, V7, V9, this V8, V6, V2, V3, V4, V5, V10, V11, V12, V13. So let's take a look at this. And let me write some questions down. What is the level of V4? And also, what's the level of V12, let's say? Yes. So once again, I'm going to write down the question and you can work through the problems and you can stop the video and work through the problems. Then I'll go through the answers. And what is the height of the tree? What is the parent of V5? And let's say V8. So it's asking what's the parent of V5, what's the parent of V8? What are the children V5. What are the descendants of V1? What are the siblings of V12? And also, let me ask the same question. What are the siblings of V1? More questions? How many leaves? And remember what those are: terminal vertices are on the tree. And then finally, what is the level of V0? So go ahead and try to do those problems. You go ahead and stop the video and then work all the problems out, or you can do them one at a time and stop the video between each answer, and I'll go through the answers. So hopefully you stop the video and work these through, or at least you're going to work one of them one at a time. So let's take a look at these. So once again, we're calling V0 the root. So what is the level? Oops, I've got my papers here. Excuse me. What is the level of V4? So again, see how far V4 is from the root. So if you start the V at the root V0, you go through one edge, two edge. So 2 is the level of V4. The level of V12, start at the root here, go one edge, two edge, three edges. So the level of V12 is 3. So again, it's just the number of edges that you have to go through to get from the root to the vertex in question. Then the height of the tree is going to be the longest path from the root to any of these. So let's see. So over here, in fact, we already saw that they go from V0 to V12. It's going to take 1, 2, 3. Same thing with any of these here. So take 1, 2, 3 to get to here. How about on this side over here? 1, 2, 3 to get to V8. 1, 2, 3 to get to V. Now it looks like the longest path is going to be 3 to any vertex. So the height then is going to be 3. And then what is the parent of V5? Just look here. So V5 is here. And its parent is V3. And what is the parent of V8? Look over here. V8, its parent is V7. And what are the children of V5? Over here, V5, you can see its children are V10, V11, V12, V13. And what are the descendants of V1? So remember, it's descendants are anything below V1. And so let's see here. We have V6, V7, V8, V9. Those are the descendants of V1. And what are the siblings of V12? Remember, the siblings are any vertices that have the same parent. And of course, you can see that's going to be V10, V11, V13, huh? So again, the siblings V12, V10, V11, V13. Now, what are the siblings of V1? Siblings of V1, again, ones that have the same parent. Of course, V1 has a parent V0, and so does V2 and V3. So it looks like the siblings of V1 are going to be V2 and V3. Like that. And the next question, how many leaves or terminal vertices are there on the tree? And again, remember the leaves are vertices with degree 1. That'd be 1, this one here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Don't miss this one up here. So it looks like that is 9. And finally, what is the level of V0? So remember, the level is the number of edges to go from the root, which is V0, to V0. Of course, there's none, right? Because V0 is the root. So those are some questions to kind of help us understand the definitions. So let's carry on with just a couple more things. Let's look at binary trees. Let's see, I have a little problem by focusing here. There, I think you got it. Okay, binary tree. A binary tree is a rooted tree in which every parent has at most 2 children. Binary tree is a rooted tree in which every parent has at most 2 children. So you can say this one here. So this is a binary tree. This is not a binary tree. Because you see, this parent has 1, 2, 3 children. Now remember, you can have less than 2, like this one over here. This one had just 1 child, but the thing is, it has at most 2 children. So this one's not binary. And this one actually is binary because this has 2 children, this has 2 children, this has 2, this one has 2, this one just has 1, 1, so this is binary. And actually, again, I'm not sure if we're going to use this a whole lot, but each child in a binary tree is designated a left child or a right child. And of course, by definition, binary tree, every parent has at most 1 left and 1 right child. Since it has at most 2 children, it would at most have 1 left and 1 right child. Now we have also something called a full binary tree. A full binary tree is a binary tree in which each parent has each parent has exactly 2 children. Full binary tree is a binary tree in which each parent has exactly 2 children. So once again, some examples here. So again, full binary tree. You can see this one's full binary tree. Because each parent has exactly 2 children. Over here, you can see because of this one, this is not, this is binary. But not full binary. It's binary because each parent has no more than 2 children, but not full binary because this one only has 1 child. So let's just have a couple more theorems here. And so theorem. And this theorem here. Suppose T is a full binary tree with K internal vertices. Then 1 T has a total of 2K plus 1 vertices. So the full binary tree, it has K internal vertices. Remember, internal vertices, those vertices have degree more than 1. Then its total number of vertices is going to be 2K plus 1. And number 2, as you might have guessed, T has K plus 1 leaves. Remember, the leaves are vertices of degree 1. So if it has K internal vertices, these are vertices of degree more than 1. And if it has K plus 1 leaves or K plus 1 vertices of degree exactly 1, then K plus 1 gives us a total of 2K plus 1 vertices. And another theorem. Suppose T is a full binary tree with height h and t leaves. In other words, t number of leaves. Then t is going to be less than or equal 2 to the h power. Or if we take the log of base 2 to both sides, of t is less than or equal to h. Another theorem. Full binary tree of height h has at most 2h leaves. Full binary tree of height h has at most 2h leaves. So those are some theorems for binary trees.